In the last couple of videos, or the last few videos, I should say, what we've done with finding the area between two curves has been fairly consistent as far as we had a couple of polynomials that we were working with, and we had to simplify the integrand before we actually did the integration to find our total accumulated area between the curves. Well, we're still going to be doing the same thing in this video. However, the types of functions that we're going to be looking at are going to be somewhat different, and the method by which we're going to find the area between two curves isn't necessarily going to be the same all the time. So let's take a look at what we're going to be talking about here. The first thing that we're seeing in this example, it's asking us to find the area of one of the regions bounded by the sine and cosine curves. So the sine function, if you're not up to snuff on what your trig functions look like, always starts at the origin. So the sine function is this one here, where I'm tracing out the one period in yellow. And the cosine function always starts at its peak positive value, where it starts at 1 here, goes down to its minimum peak value, and then comes back up here to again complete one period of the periodic function. So f of x, there's nothing saying that one has to be another, but I'm going to say that the f of x function is going to be the sine function. So let's pick another color here. So this will be sine of x, and g of x will be cosine of x. And it's very easy to manipulate one function to become another function. They're essentially the same thing with just slightly out of phase with one another. So here, the yellow function, this is your f of x, and the red one is the g of x. Now, it's asking us to find the area between one of the regions. So one of the regions is essentially kind of this area here, because what we have on that one and what we would have in, say, this region here, they're going to be the same. Because the functions are periodic, it's just you could think of them as the same thing across a vertical line of reflection. But how do we identify those? Well, same thing like what we had to do in a previous video, was we needed to know where are the intersections here. So I need an intersection here, and I need an intersection here. And we're not going to determine what these intersections are algebraically by setting one function equal to another function. We're going to just use the periods or the critical points that you would have for a trig function. So following the graph here, here we have, we have pi right here in the middle. And let me try and pick a brighter color here. Here we have, pi, and it's still giving me the same color. It didn't change color. There we go. There's pi, and there's 2 pi, and of course we have 0. So somewhere in between, come on, give me 0. So in between, we're going to need to be able to identify what the rest are. Well, here with my other critical functions, this part right here at the midline of the sine function or the cosine function, this is going to be pi over 2. And right here, that is going to be, what was it, 3 pi over 2. So that will allow us to kind of see, well, where are these functions going to be intersecting? And if you want to, you can kind of pull out a unit circle and kind of see where they're going to be at. But this intersection right here, that is going to work out to be pi over 4. And the intersection that we have right here that we're looking at, which I'll come down here and write that one, that is going to be a 5 pi over 4. And those are the 2 points that we're going to use to help us determine the interval of our function. So here we're going to look at the interval a to b. So we're going to say from pi over 4 to 5 pi over 4. Okay. And the last thing it's asking us to do now is to go ahead and integrate it. So we know the two functions, and we know the points that determine the interval now. So that is going to allow me, and let me pick another color for this. That's going to allow me to be able to write a function here where I'm going to be able to integrate it. So I'm going to say a, just generically for area, is going to be equal to the definite integral of pi over 4 to 5 pi over 4. And we're going to say, uh, we're looking at the first function here. This is kind of what we're talking about here, where we're going to say that the f function is going to be greater or above the g function. So I'm going to say f was sine, so I'm going to say sine of x minus cosine of x dx. Now, for the integration itself, there's really nothing to simplify for this function because sine and cosine are not like terms. So we're going to go ahead and take the antiderivative of both pieces. So the antiderivative of sine, well, let me go ahead and put my definite integral here, pi over 4 and 5 pi over 4. So the antiderivative of sine is going to be negative cosine of x, and the antiderivative of cosine is just going to be sine. So the negative doesn't change, so this is going to be minus sine of x. And I don't know why I'm writing my integral here. Some of you are probably, why are you doing that? Because I'm kind of operating on less sleep than I would care to admit at this moment. Okay, so that is going to be the antiderivative, sine of x. There we go. And we're evaluating it from pi over 4 to 5 pi over 4. And this is where things can get a little tricky as far as making sure that you remember your unit circle all the way through and not just, where it's going to be a 0 or 1. So in this case, we start substituting. So I'm going to say, okay, well, let's say negative, 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 come on, right? Cosine of 5 pi over 4 minus, close your parentheses, sine of 5 pi over 4. And we're going to subtract negative cosine of pi over 4 minus sine of pi over 4. So this is where if you don't remember your unit circle, you definitely need to make sure that you refer back to it. So the negative uh, on the cosine is going to tell you the direction that you go, whether you go clockwise or counterclockwise, but you're still going the same rotation, the same amount of radians. So this negative cosine of pi over 4, that's going 5 pi over 4 is going to put you at negative radical 2 over 2. So negative cosine of 5 pi over 4, the negative and the negative will give me a positive radical 2 over 2. And the same thing with the sine. Sine of 5 pi over 4 is going to be negative, but I multiply it by the negative on the sine itself, and that'll be plus, I wanted to write 5 pi again for some reason, and it'll be plus radical 2 over 2. Okay, so there's our first difference. And we do the same thing with the other one at pi over 4. So at pi over 4, this is going to remain negative radical 2 over 2, radical 2. And same thing with sine. In this case, it's going to remain negative radical 2 over 2. Well, inside of each set of parentheses here, they are like terms. So the numerators are going to give me 2 radical 2 over 2. And of course, the 2's are going to simplify to be 1. And we'll go ahead and do the same thing here. I'm going to get negative radical 2 radical 2 over 2. And again, the 2's are going to simplify to be a 1. So here I'm going to be left with a positive radical, come on, radical, why won't you write anymore? There we go. Why won't you write? Right, no, just doesn't want to write there. Huh? Radical 2 and the negative, the double negative. Sorry, I don't know why it doesn't want to write here. The double negative minus the negative radical 2 will be positive, positive radical 2, giving me total of 2 radical 2 for my area, the one area between the two trig curves. Now the next one that we're going to look at here, it's going to be looking at it from the y-axis instead of the x-axis, and that's a big difference. That's a big shift. Okay, so if you notice, our functions are written in terms of x is equal to something with y, where y is kind of acting as our independent variable in this case. Now the functions themselves, or the process, really isn't going to be any different. You're still going to look at the function, how taking the difference of one from the other. So here, with the functions that we have, we're going to say, the way that I know I'm going to subtract one from the other is, let's look at it. Let's take something like this, and let's imagine that it was in written or graphed in terms of x. Okay, well we can see that the parabola piece is kind of above the linear piece for the region that we're going to wind up being looking for. So I'm going to subtract the linear piece from the parabolic piece. Okay, and so that is going to give me, in this case, I'm going to again just kind of say a, oh, oops, if I turn my pen back on, a for area, and I'm going to be integrating it. Now again, I need to know where the intersections are, and the intersections are very clearly marked in this case, but of course we're looking at it in terms of what's the smallest y number to what's the biggest y number. So the smallest y number is at negative 2, and the biggest y number is at a positive 1. Okay, so those are that is how we determine the interval, is from the lowest y value to the biggest y value, just like what we do with x's. And so now I'm going to say 3 minus, all right, this is starting to get irritating. My computer doesn't want to acknowledge that I'm trying to write on it anymore. Minus y squared, and we're going to subtract the y plus 1, and we're going to write it dy instead of dx. So we have our integral from negative 2 to positive 1 on the y-axis. The 3 minus y squared, there's really nothing to do with that now. 3 minus y squared, distribute the negative, and I'm going to get minus y minus 1 dy. So putting it in standard form, that's just something I like to do before I try to do any integration here, is going to give me a negative y squared minus y plus 2 dy. And now we will do the integration the way that we would normally do. And there's the tricky spot that kept picking up my palm on the screen there. So now we're going to do our integration, or the antiderivatives, the way that we would normally do it. So here the antiderivative of negative y squared is going to be negative 1/3 y cubed. And then I'm going to get minus 1/2 y squared, and then plus 2y. And we're evaluating it from -2 to 1. And we continue from this point doing it the way that we have been doing it in the last several examples. Substitute the positive 1 first. So I'm going to get negative 1/3 times 1. 1 cubed is still just going to be 1. Minus 1/2 times 1 squared plus 2 times 1. And now we'll do the same thing with the -2. So I'm going to get negative 1/3, -2 cubed, minus 1/2 times -2 squared, plus 2 times -2, and see what we wind up getting. So all of the stuff in the first parentheses, -1/3, minus 1/2 plus 2, that's all going to simplify to be a 7/6. And then we're going to subtract the other one. So that's going to be like essentially a positive 8/3 minus 2 plus 4. And we're going to wind up with this one to be a negative 10/3. So 7/6 plus 10/3 is going to give me my final accumulated area, in this case, of 27/6, or 4.5 units. Okay, and that's where we're going to stop for this video. There will be one more that we want to go through, but again, I'm trying to keep the individual video lengths to be somewhat tolerable. But thanks for watching, ladies and gentlemen. Take care.